Okay, so let's take a look at some solutions to a couple of momentum problems that deal with both momentum and kinetic energy. So the first problem is question number 8. So unit 2, number 8, what we have are two blocks. One that's 2 kilogram, one that's 4 kilogram. The one that's 2 is moving to the right 6 meters per second. The one that's 4 kilograms is moving to the left at 4 meters per second. It's always helpful to draw a diagram. It will help you keep track of signs later and just get a sense of what's going on. So that's what we have at the beginning. And then after the collision, it says that we have the 2 and the 4 stuck together because this is a perfectly inelastic collision. And then what is the final velocity? Is it moving to the left? Is it moving to the right? We don't really know. We're going to solve the problem to figure it out. So we're looking at conservation momentum because we have no external forces acting. We just have the two blocks that are coming together. So we remember our formula, and I write it out as m2v2, meaning the mass of the 2 kilogram times the velocity of the 2 kilogram, plus the mass of the 4 times the velocity of the 4 kilogram, equals the mass of the two velocities together, times, and I'm just calling it v prime, the velocity that those things are going to go with together. We're going to solve to try to find v prime. So we'll plug in our values. We got 2 kilograms and 6 meters per second. We've got 4 kilograms and a negative 4 meters per second. It's really important to remember that negative sign because that means that the block is moving to the left. This is how we're keeping track of this in terms of vectors. Now we just have some algebra to do, so we can figure out we got 12 on the left and a negative 16. So we'll add those up, and we still have the 6 kilograms times v prime. So we get negative 4 kilogram meters per second. We're going to divide that by 6 to solve and get v prime is equal to negative 0.67 meters per second. So the two blocks together will be moving to the left at about 2/3 of a meters per second. All right. Now we got to figure out the kinetic energy, the change in kinetic energy, because not only these things are we going to have a change in momentum, but we're going to have a change in energy potentially. So let's find out. So we say kinetic energy, the change is going to be the kinetic energy final minus the kinetic energy initial. Now if we remember, the formula for kinetic energy, which is the energy associated with a moving mass, is 1/2 mv squared. So we want to find the kinetic energy of each block before and then each block after and find out what the difference is between the two. So here we go. We're going to start with the final. We go 1/2 m, we've got 6 kilograms because the 2 and the 4 are moving together, times that negative 0.67 meters per second squared. Now notice whenever you square a negative, that the negative goes away. So really, the signs when we're doing kinetic energy don't make any difference. It's just about how fast are they going, which is really nice. You don't have to worry about signs. But you do have to remember to square the velocity term. So we square the velocity term and only the velocity term, then we multiply it by the mass in 1/2. So we get 1.35 joules. So that is the final kinetic energy. Now let's go back and figure out the initial kinetic energy. What we got is 1/2 times the 2 kilogram, and it was initially moving at 6 meters per second. And then we got the 4 kilogram, which was moving at negative 4. But again, if we square that, that negative goes away. So when we add all of that up, we're going to get 68 joules. So it started off with 68 joules of energy and ends up with only 1.35. So even though momentum is conserved, a lot of energy was lost. And that is typical in inelastic collisions. When there's a collision and two things stick together, you have a lot of energy lost as heat or sound, but energy will be lost. So we can conclude that because the change in kinetic energy is negative, we're losing energy, we can conclude that this must be an inelastic collision, which we already knew because it's stuck together. But that's what happens with the energy for this particular scenario. So let's move on. Next problem we're going to take a look at is number 9. So very similar, we have two blocks. We have a 2 kilogram block that starts moving to the right at 6 meters per second, and we have a 6 kilogram block that's not moving at all. And then after the collision, we're going to get a 2 kilogram that's moving to, well, we assume it's going to move to the left because they're going to bounce off each other. I'm guessing it's going to go left. And then we know that the 6 kilogram is moving to the right at 3 meters per second. Again, drawing these diagrams is really helpful to help us keep track of signs. And then we typically say to the right is positive, to the left is negative. So let's go ahead and solve the momentum part of the problem. We're going to lay it out 2 kilograms times 6 plus 6 kilograms times 0. So that whole term is going to go away. So that's going to become 0, is equal to 2 kilograms times v1 prime. And that's what I'm calling this velocity here, v1 prime. It's the initial velocity of the first block after the collision. That's what the prime indicates after the collision. plus 6 kilograms times 3 meters per second, and that's positive. So now we have to do some algebra, and we're going to solve. So we get 12 kilogram meters per second is going to be equal to 2 kilograms times that V1 prime, plus that 18 kilograms from the block on the right. So now we're going to have to solve and isolate V1 prime, subtract 18 from both sides. I get negative 6, and then I'm going to divide that by 2, and I will get that velocity 1 prime is negative 3 kilogram meters per second. So I was right in my guess that V1 is going to be moving to the left, and it's going to be moving to the left at negative 3. Oops, that's not kilogram meters per second. Let's fix that. That's not kilogram meters per second. It's just meters per second, because velocity doesn't have a kilogram in it. It's just velocity. So fixing that, 3 meters per second. Better. Okay, now we want to find out what is the change in kinetic energy for this scenario. Again, kinetic energy, delta KE, the change in kinetic energy is KE final minus KE initial. And KE is 1/2 mv squared. So let's find the initial energy for each term and the final energy for each term and see what happens. So here we go. I'll start with KE final. That's going to be 1/2 times that 2 kilogram times that negative 3 that we just found. We're going to square that term, plus 1/2 times 6 times 3, and square that term. And then we do the algebra, and we get that the kinetic energy final is 36 joules. Let's go ahead and find the kinetic energy at the beginning. Initial is going to be 1/2 times that 2 kilogram. The initial velocity was 6 meters per second, so we're going to square that, plus 1/2 times 6 kilograms times 0 squared, because that thing wasn't moving. And we get 36 joules. So what we find in this problem is that the energy hasn't changed in the collision. We say that the mechanical energy is conserved. We had 36 joules to start, we had 36 joules to finish, no energy is lost, and that is a special case. And when that is true, we say that we have a perfectly elastic collision. So it's if these things had little magnets that repelled each other and they bounced off each other without touching. There was no sound loss, there was no heat loss, they just perfectly bounced. Now that scenario is actually not typically, I mean, it's really difficult to get something that's perfectly elastic, but you can get pretty close with some types of collisions. And that concludes our solution to these two homework problems.